Operations. In MATLAB. 1. Objective. This lab focuses on the creation of discrete time signals in MATLAB and explains the required MATLAB commands. After performing the lab, the students will be able to create discrete time signals in MATLAB. Use MATLAB commands to perform simple operations on discrete time signals. 2. Resources required. A computer. MATLAB 7.0 or higher. 3. Introduction. Digital signal processing involves the processing of a discrete time signal, input signal, to produce another discrete time signal, output signal, which has some desired properties. A strong background of discrete time signals is essential for analyzing discrete time systems. Following are some of the commonly used discrete time signals generated using MATLAB. 3.1 Unit impulse and unit step sequences. A unit impulse sequence of length n can be generated in MATLAB by the following command. N equals 10. U equals 1 zeros, 1, n 1. A unit impulse sequence delayed by m samples where m equals 5. UD equals zeros, 1m, 1 zeros, 1 nm, 1. Likewise, a unit step sequence Sn of length n can be generated using the MATLAB command. S equals 1s, 1n. A delayed unit step sequence can be generated in a manner similar to that used in the generation of a delayed unit sample sequence. Program P1_1. Generation of a unit sample sequence. Clear all. Close all. CLC. Generate a vector from -10 to 20. N equals -10:20. Generate the unit sample sequence. U equals zeros, 1,10, 1 zeros, 1,20. Plot the unit sample sequence. Stem, NU. Slabel, time index n. E-label, amplitude. Title, unit sample sequence. Axis, -10-20-01.2, grid on. 3.2 Sinusoidal sequences. Sinusoidal sequences can be generated in MATLAB using sin and cos functions. Program P1_2 is a MATLAB code that generates a sinusoidal signal. Digital signal processing lab page 3. Program P1_2. Generation of a sinusoidal sequence. Clear all, close all, CLC. N equals 0.40. F equals 0.1. Phase equals 0. A equals 1.5. Arg equals 2 pi Fn, phase, x equals a cos, arg. Stem, nx, r, plot the generated sequence. Axis, 0.40-22. Grid. Title, sinusoidal sequence, slabel, time index n, e-label, amplitude. 3.3 Linear and nonlinear systems. We now investigate the linearity property of a causal system. Consider the system given by 0.41 plus 0.752 equals 2.2403 plus 2.49081 plus 2.24032. MATLAB program P1_3 is used to simulate the system, to generate three different input sequences. x1n, x2n, and xn equals a, x1n plus b x2n, and to compute and plot the corresponding output. Sequences y1n, y2n, and yn. Program P1_3. Generate the input sequences. Close all, clear all, CLC. N equals 0.40, A equals 2, B equals -3. X1 equals cos, 2 pi 0.1 asterisk n. X2 equals cos, 2 pi 0.4 asterisk n. X equals a x1 plus b x2. number equals 2.2403 2.4908 2.2403. Den equals 1 minus 0.40.75. IC equals 00, percent set 0 initial conditions. Y1 equals filter, number den x1 IC, percent compute the output Y1N. Y2 equals filter, number den x2 IC, percent compute the output Y2N. Y equals filter, number den x IC, percent compute the output Yn. Yt equals a Y1 plus b Y2. D equals YYT, percent compute the difference output Dn. Percent plot the outputs and the difference signal. Subplot, 3,1,1. Stem, ny. E-label, amplitude. Title, output due to weighted input, a \x_1n plus b \x_2n. Subplot, 3,1,2. Stem, nyt. E-label, amplitude. Title, weighted output, a \y_1n plus b \y_2n. Subplot, 3,1,3. Stem, nd. E-label, amplitude, Digital Signal Processing Lab page 4. Slabel, time index n. Title, difference signal. 3.4 Time invariant and time varying systems. We next investigate the time invariance property of a causal system. MATLAB program P1_4 is used to simulate the system, to generate two different input sequences, xn and xnd, and to compute and plot the corresponding output sequences y1n, y2n, and the difference y1n, y2n plus d. Percent program P1_4. Percent generate the input sequences. Close all, clear all, CLC. N equals 0.40, D equals 10, A equals 3.0, B equals -2. X equals a cos, 2 pi 0.1 n, plus B cos, 2 pi 0.4 n. XD equals zeros, 1D, X. Number equals 2.2403 2.4908 2.2403. Den equals 1 minus 0.40.75. IC equals 00, percent set initial conditions. Percent compute the output Yn. Y equals filter, number den x IC. Percent compute the output Ydn. Yd equals filter, number den x DIC. Percent compute the difference output Dn. D equals y, yd, 1 plus d 41 plus d. Percent plot the outputs. Subplot, 3,1,1. Stem, ny. E-label, amplitude. Title, output Yn. Grid. Subplot, 3,1,2, stem, nyd, 141, E-label, amplitude. Title, output due to delayed input xn, number 2 str, d. Grid. Subplot, 3,1,3. Stem, nd. Slabel, time index n. E-label, amplitude. Title, difference signal. Grid. 3.5 Impulse response computation. The MATLAB command y equals imps, number den n, can be used to compute the first n samples of the impulse response of the causal Lti discrete time system. MATLAB program P1_5 given below computes and plots the impulse response of the system. Percent program P1_5. Percent compute the impulse response y. CLF. N equals 40. Number equals 2.2403 2.4908 2.2403. Den equals 1 minus 0.40.75. Y equals imps, number den n, Digital Signal Processing Lab page 5. Percent plot the impulse response. Stem, y. Slabel, time index n. E-label, amplitude. Title, impulse response. Grid. 3.6 Convolution. The convolution operation is implemented in MATLAB by the command conv, provided the two sequences to be convolved are of finite length. For example, the output sequence of an first system can be computed by convolving its impulse response with a given finite length input sequence. Equals sigma. Infinity. Equals infinity. Equals sigma. Infinity. Equals infinity. Or can be represented as equals. The following MATLAB program illustrates this approach. %program P1_6. Close all, clear all, CLC. H equals 321-210-403, impulse response. X equals 1-23-4321, input sequence. Y equals conv, hx, n equals 014. Subplot, 2,1,1, stem, ny. Slabel, time index n, e-label, amplitude. Title, output obtained by convolution, grid. x1 equals x zeros, 1,8. y1 equals filter, h1 x1. Subplot, 2,1,2, stem, ny1. Slabel, time index n, e-label, amplitude. Title, output generated by filtering, grid. 3.7 Stability of Lti Systems. As indicated, an Lti discrete time system is bibostable if its impulse response is absolutely sum-able. It therefore follows that a necessary condition for an IIR-Lti system to be stable is that its impulse response decays to zero as the sample index gets larger. Program P1_7 is a simple MATLAB program used to compute the sum of the absolute values of the impulse response samples of a causal IIR-Lti system. It computes n samples of the impulse response sequence. Evaluates. Equals sigma. Equals 0 Digital Signal Processing Lab page 6. For increasing values of k, and checks the value of hk at each iteration step. If the value of hk is smaller than 10⁶, then it is assumed that the sum s, k, of equation has converged and is very close to s, infinity. %program P1_7. Stability test based on the sum of the absolute values of the impulse response samples. Clear all, close all, CLC. Number equals 1-0.8. Den equals 1.50.9. N equals 200. H equals imps, number den n plus 1. Parsum equals 0. For k equals 1 n plus 1. Parsum equals parsum plus abs, h, k. If abs, h, k. Break. End. Plot the impulse response. N equals 0 n. Stem, nh. Slabel, time index n. E-label, amplitude. Print the value of abs, h, k. DISP, value equals. DISP, abs, h, k. 3.8 The moving average system. Equals. 1-3. +1 ++1. Examination of above EQ. Reveals that the 3-point smoothing filter considered here is an LTI first system. Moreover, as yn depends on a future input sample xn plus 1, the system is non-causal. A causal version of the 3-point smoothing filter is obtained by simply delaying the output by one sample period, resulting in the FIR filter described by equals 1-3 +1 +2, 1 equals 1 sigma 1 2. This defines a causal M-point smoothing FIR filter. The system of EQ 2 is also known as a moving average filter. We illustrate its use in filtering high-frequency components from a signal composed of a sum of several sinusoidal signals. Program P1_8. Generate the input signal clear all, close all, CLC. N equals 0:100. S1 equals cos 2 pi 0.05 n, % a low frequency sinusoid. S2 equals cos 2 pi 0.47 n, % a high frequency sinusoid. X equals S1 plus S2. Implementation of the moving average filter digital signal processing lab page 7. M equals input, desired length of the filter equals number equals ones, 1m. Y equals filter, number 1x, /m. Display the input and output signals. Subplot, 2,2,1, plot, NS1. Axis, 0, 100, -2, 2. Slabel, time index n, E-label, amplitude, title, signal #1. Subplot, 2,2,2, plot, NS2. Axis, 0, 100, -2, 2. Slabel, time index n, E-label, amplitude, title, signal #2. Subplot, 2,2,3, plot, NX. Axis, 0, 100, -2, 2. Slabel, time index n, E-label, amplitude, title, input signal. Subplot, 2,2,4, plot, NY. Axis, 0, 100, -2, 2. Slabel, time index n, E-label, amplitude. Title, output signal. Lab worksheet, lab number 1. 1. Run the program P1_8 for m equals 2 to generate the output signal with xn equals S1n plus S2n as the input. Which component of the input xn is suppressed by the discrete time system simulated by this program? 2. If the Lti system is changed from yn equals 0.5, xn plus xn, 1, to yn equals 0.5, xn, xn, 1, what would be its effect on the input xn equals S1n plus S2n? 3. Run program P1_8 for other values of filter length m, and various values of the frequencies of the sinusoidal signals S1n and S2n. Comment on your results. 4. Use sinusoidal signals with different frequencies as the input signals and compute the output signal. For each input, how do the output signals depend on the frequencies of the input signal? 5. Run program P1_3 and compare yn obtained with weighted input with ytn obtained by combining the two outputs y1n and y2n with the same weights. Are these two sequences equal? Is this system linear? 6. Consider another system described by yn equals xn xn1. Modify program P1_3 to compute the output sequences y1n, y2n, and yn of the above system. Compare yn with ytn. Are these two sequences equal? Is this system linear? 7. Run program P1_4 and compare the output sequences yn and ydn, 10. What is the relation between these two sequences? Is this system time invariant? 8. Consider another system described by modify program P1_4 to simulate the above system and determine whether the system is time invariant or not.